Bismillahirrahmanirrahim. Derivative of a quotient of two functions, that is generally known as the quotient rule. F of x by g of x whole derivative equals to g of x into derivative of f of x minus f of x into derivative of g of x whole divided by g of x whole square. We are going to prove this quotient rule. We are going to prove the quotient rule by the first principle. So let's take y equals to f of x by g of x. Y plus del y becomes f of x plus del x divided by g of x plus del x. Then we evaluate del y by subtracting y from both sides and now put y equals to f of x gx. And you can see we can take the LCM now. So we take the LCM and we get this result. Del y is equal to f of x plus del x into gx minus f of x into g of x plus del x divided by g of x plus del x into g of x. Now we are going to subtract and add f of x and into g of x in the numerator. We will subtract f of x gx here and we will add it here. We will write minus f of x gx here and we will write plus f of x gx here. That is, we are going to subtract and add f of x g of x in the numerator. So you can see we get del y is equal to f of x plus del x into gx minus f of x gx minus f of x into g of x plus del x plus f of x g of x. That is, f of x dx has been added and subtracted here. Now we can see g of x is common in these two terms and f of x is common in these two terms. So we are going to take these common and we get del y is equal to g of x multiplied by f of x plus del x minus fx minus f of x multiplied by g of x plus del x minus g of x whole divided by g of x plus del x into gx. Now we go for the next step of first principle method, which is divide both the sides by del x. So we divide both the sides by del x and now we are again going to make some adjustment. We are going to rewrite the same expression and now this time we are going to write this del x under this numerator like this. This del x will be written under this and this del x will be written under this. You can say it like this: del y by del x as it is gx and the del x which was here, it has been written under f of x plus del x minus fx. Then we have minus fx and del x is again written in under g of x plus del x minus g of x. And now we apply the limit when del x tends to 0 and where we are going to write it. We are going to write limit here and we are going to write limit here and here and here and here and here. Let's see. Limit when del x tends to 0, del y by del x equals to limit when del x tends to 0 of g of x, then limit when del x tends to 0 of this expression, then minus limit when del x tends to 0 of f of x, and then limit when del x tends to 0 of this expression. And in the denominator, limit when del x tends to 0 of this. What will be the results of these limits? This will become dy by dx. This does not have any del x, so it will remain gx. This will become d by dx of f of x. This does not have any del x, it will remain fx. And this here will become d by dx of gx. This will become g of x plus 0 into gx, that is gx into gx. So it will become g of x whole square. So what is the final result? Dy by dx is equal to g of x into d by dx of fx minus f of x into d by dx of gx whole divided by g of x whole square. You may write it in the shape of prime, which is f of x by g of x whole prime is equal to gx into f prime x minus fx into g prime x whole divided by g of x whole square, and the quotient theorem is proved.